All right, ladies and gentlemen, we're back. Finally, we're going to crush anti-derivatives in a bigger kind of way. We're going to get some examples in, and I'm going to show you why having an estimation is sometimes necessary, rather using a Riemann sum is sometimes necessary rather than having a direct integral. Because if you have a direct integral, then you can do it exactly. So it makes you question, why would you abandon exactness for an estimation? Because some things you just cannot calculate. All right, let's talk about a few examples here. Quick one, was hit hard. All right, so this thing is asking me let's see here, is asking me, it says oil leaks out of a drum onto the floor at a rate of T times T to the negative 2 gallons per minute. Okay, so they're telling me that this function, and I don't even know what that looks like. That's icky, yuck. Where T is minutes as it starts, after it starts to leak. So the question is how much leaks out during the first 10 minutes. So they're asking me to find the net change of how much it leaks over the first 10 minutes. Well, what defines the rate over that first 10 minutes as time changes? And it's dx because this is a equation in time. Well, that's going to be the net change, right? So the integral of the rate of change will always be the net change. Okay, so but the rate of change here is based off this function t times T to the negative 2. Now, this is the big deal. Does anybody have you guys have just started integrating for real, kinda, and now this is something that before took product rule or chain rule, right? If we were to take a derivative of something like this is a much more complex derivative than we're able to, or integral that we're able to handle, or antiderivative integral, same thing, that we're able to handle. So what do we have to do here? Well, my best bet is, you know what? Let's just estimate this. I don't know why I always do that. Let's just estimate. Let's just estimate this. Okay? Well, we're going from 0 to 10. This is what Riemann's contribution was, I think, was just how to organize the thoughts. And he said, well, we're going from 0 to 10, right? So I'm going to divide this, in, let's say, into 5 equal pieces. So that means it'll go 2, 4, 6, 8, 10. And what Riemann basically said is that if, let's say we were going to do like a L 1, 2, 3, 4, 5, 5, right, to estimate this, right, because that's the left-hand side Riemann sum, that's what it stands for. He said, well, you know the bases of all these are 2, right? So this is going to be equal to just the base times the height. Well, now that's where it gets a little tricky, because the heights are going to change according to each one. So he says, well, let's say we do the left side. Well, that'll give me how tall my rectangle will be on this side. And that'll give me how tall it's going to be on this side. And then I can just add all those things up, and then that'll be an okay estimation. He's right. But how do I get that? I'm going to call this F for good measure. That'll be F, what looks like 0. So right here. Because these are the left-hand side. So this side, this side, this side, this side, and this side would be left-hand sides. But notice, this is where it stops at. So that won't be anything. So that's f of 0 plus 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6. That's why that sum notation, I almost used it earlier, but I was like, it's just overkill. F of 8, because I hate writing these long strings. But that's why that sum notation was invented, is because you get annoyed writing that very, very quickly. All right, so if we sum all of this up, what do we in fact end up getting? Well, that's a great question. I don't know, but that would be the estimation that we would get. I'm trying not to actually have to go through and plug all this crap in, but it looks like I'm going to have to. This is 2 times, see, plug in 0, that's 0, easy. Plus 2 times, let's see, that's going to be 2 times 2 to the negative 2 is 1/4, which that makes that just a half. So this whole thing is a half. Yeah, I try my best to avoid calculations. I feel like calculations can get me tripped up. So let's plug in 4 times 1/16, that's a quarter. Plus 6 is 6 over 2 to the 6, which is 64, which is 3 over 32. Yuck. You guys see how technical this is, but I think it's worthwhile. Plus finally f of 8, 8 times, yikes, so that's 16 times 2 to the 8 is 256, 512. So add this up, and this drops out. Add these up, and it tells you approximately how many gallons which will mix. Okay, I'm going to leave that up to you guys to figure out, but I'm not going to waste video time for that. You guys can figure that stuff out. But that's how you get a good estimation of what this integral was, which is our job. Okay, let's move it forward. Okay, let's try something else. This one came from an old final exam. So write down and evaluate the Riemann sum with 6 terms. So we're trying to get 6 rectangles here. That gives us a lower estimate of that. Lower estimate means we have not overshooting it. It's an underestimate. So remember what I said before? A left side most of the time is your underestimate. So I always say try your left side first. Okay, so here we go. Actually, no. Won't it be an overestimate? If I do a left side, this looks like that. Yeah, that'll be an underestimate. So it's always good to know the graph and what's going to happen to it. So left side's where I'm going to go with. So they said 1 to 3 are my intervals. So I need to break this up into, let's see here. 1 to 3, that means this is 2. That means this is 1 and 1/3. So 4/3 plus, my goodness, it's a third, add another third, 5/3, 6/3, 7/3, 8/3. You can see how tedious this can be. So the base of these rectangles are 1/3. That's regardless, right? The heights are the ones I'm trying to take it easy on. So an L left side 6 is what we're doing. The base here is 1/3. The height will be determined by the output at 1. All right, I'm not going to waste your guys' time on calculating the output. I'm going to let you figure that out, even though I do think it is a very easy task to do. Except when we start plugging in 4/3, right, as our second height, that can be tedious. Plus another base of 1/3, we're plugging in the left-hand side of the rectangle, which is f of 5/3. And then finally, 1/3 times f of 2. So you notice that the bases are all 2. So you'll notice sometimes they'll just say add all the outputs up and it's multiplied all by 1/3. I'm just doing this to be excessive because I do believe in not shortcutting the understanding for ease of process. I think that's where most of society has missed out on quite a bit. They think that just because you get an upgrade and you can get to an answer faster, that you retain the same understanding. Totally untrue. All right, so if you nail all this, I don't know what you get, but I'll guarantee you this, that whatever answer you get here, we'll call it smiley face, right, which was the L6 that we just calculated. That's only an approximation of what exactly the integral from 1 to 3 of square root of 6x plus 2 would be, right? So that's what that'll give you. Okay, so you notice the calculation is not the part I want to scare you about. It's really about, because all you're doing is finding those rectangles. You're finding those little rectangles. That's all you're doing, because there's a curve that you don't know the area of. That's underneath, and you're trying to get an approximation for it. All right, so anywho, let's move it forward. This should be one of the last slides I do with you, okay? So this is actually a really cool one because all I gave you are points. So suppose you have a function, and I want you to approximate the area under the curve of that function. So what does that tell you? Well, here we go. Let's graph it a little bit. I tell you at -2, it's -2. So this point right here. I tell you at -1, it's 1 though. Now I don't tell you how you get there though. That's the crazy part. At 1, it's -1. At 2, it's 2. And at 4, well, I don't even give you 3. Oh my goodness. Is -3. So you're a big loser at 4. So the question is, I need to approximate the area, right? And general idea is we always want to just break it up into rectangles. All right, well, I don't know how the dots connect. The dots could connect in many different ways, right? It could be something, let me see if I could do this without screwing myself up. I have a tendency to do this. Let's make it red. It could do something like this. Right? But the reality is that's not guaranteed, because it also could do something like this. Right? And I can also avoid myself some area that way. Remember, because we want area under the curve. And we still haven't talked about what this area means. Yes, it's a negative area. It technically does cancel out with the other stuff. because it's a negative towards the actual calculation of the area. Unless it's the difference between like speed versus velocity. Velocity is for sure just like direction and magnitude. You can tell which way it's going. Speed doesn't care, right? So I would add all the areas together if I wanted that. Anyhow, we'll talk about a couple examples when time comes. So they don't look like either one of these. Boom, boom. They don't look like either one of those. So what do I know for sure? I know I could take rectangles. So here's what I'm going to do. That base is 1. From here, I'm going to do left sides only. So this will accommodate that. So that is 1. Okay? At -1 to 2, right? That, from here to here, this point is 1. That point was -1. So the base is 2. What's the height of this? The height at -1 was 1. So this is 2. And all I'm going to do is I'm going to add these areas up. That's the best approximation I can give. So this one is 1. From there to there is 1. So that's 1. Right? It's really commonsensical that with a Riemann sum, all you do is estimate the area of the curve. What makes it even more interesting is estimating that area means something. It could be a rate of pay, dollar amount. It could be something, right? So you always want to know what that something is. So at 2, it's 2, so that's 1, that's 2, so this is 2, easy. Okay, I'm just doing basic multiplication here. I'm not doing anything else. And from 2 to 4, where this is, oops, I messed something up. Oh, crap. Now what do? I'm doing left side. So I go 2 to 4, here to here. And why do I need to do that? Is 2, and this is 2, this is 4. So this last point at the end doesn't get used because that would be on a right-hand side, right? And we can actually do the right-hand side. So this is a left, looks like 1, 2, 3, 4, L4. Well, that's going to give me 1 plus 2 plus 1 plus 4, which is just the areas, which that tells me that L4, which is the approximation of that, so the left side of Riemann sum of four rectangles big, 4, 5, 6, 7, 8 is 8, right? If you did a right 4, then let's see what we would get here. So erase all this good stuff and take it back to right here. Yeah, I think we can salvage some of this picture. Yeah, we can salvage some of it. All right, so if I do that, that means my height on the left side will be determined by the right side of these rectangles. So here's the right side, that's that. I should probably go back and plot it all. I know. All these little specks get in the way for me. I'm sorry, I'm a little OCD with it. All right, so -2, -2, but -1 is 1. So if this is an interval, now then this would be the base, okay? 1 is -1. Okay, 2 is 2. And 4 is -3. Okay, so a right-hand side, now let's take a look at a right-hand side. A right-hand side would be, well, here's the interval, here's the height. What's the height? Well, it's 1, the base is 1, so this is 1. Easy. Okay, well, what's the next one? Well, this is the next interval, right? It's the next point. That's the height. What is this? Well, that would be 0 and -1. So this is 2 and 1 is 2, right? But don't forget to be negative. And that's one thing I forgot to include on the last one. So these two values, unfortunately, were positive. This guy was negative. This guy was positive. Nope, first guy was may not be extra. First guy was positive. You know what I mean. All right, you'll figure it out. Bottom line is grab the values that I just had up here, and those are the values that go here. So it should end up being positive, negative, so negative, positive, negative. That's how it would be. So that would end up giving me 4 here instead. Sorry, guys. All right, and this, remember we're going right-hand side, so this gives me from here to there, and there to there. Now it gives me, I know this is probably irritating the mess out of you guys, but you guys will be okay. And then finally, that's my height. And this guy, it's 2. This is 4. This is 3. This gives me 6. So be careful here. So when we do this L4, I have 1 positive, -2, +2, -6. So the point in fact here is that depending on which one you did, you could have for sure had two different answers here. I didn't want to make this too long or drawn out, but it went down that way. One tells me my area is super negative, meaning that I have more area on the bottom than I do on the top. The other one says the area is super positive, right? So which one is the right approximation? The one you use, because the idea is to approximate it. So you could have gave me any one. But in the end of the day, the way you would really figure it out on what this approximately was is you'd increase the number of rectangles. Do 30, 40, 50 of them. But they only gave you enough information to do 4, right? So that's the basic gist of it. Area of the exact curve is generated by the area of these little rectangles. We take the limit until they get small enough and they go off to 0. That's beautiful. And then we get the exact area underneath that, which is an antiderivative. The antiderivative, again, is just the net change. The net change is something that we use to answer the problems of what is the how much did I grow from here to here? It's over an interval, okay? So that is basically it every single time, all right? No pain, no gain, all right, guys? I will see you guys in the next video, and we will get deeper within integration.